Hello Math Humans, we're going to do 9.1b today. We're going to be talking about summation and series. Our objectives are that we're going to do summation notation, we're going to find the sum of the series, and then we're going to do some grapher work. So I started by writing out the summation notation, and then we're going to chat about this. This is epsilon, it means sum. The bottom index is going to tell you where the sequence starts, so where we're going to start summing our sequence. The top one says we're going to stop summing here, and then a sub I is going to be the rule. So if we just write this out, this is called the rule. This is going to be where I start the summation. The top index is going to be where I end the summation. Okay, and it's actually not a complicated concept. We will do this with some formulas later, but for right now we're going to do it by hand, and then we're going to talk about doing the same example in a calculator. So let's do example number 1, and we're going to do it both ways. So we're going to find the sum by hand, and we're going to find the sum using a grapher. Okay, so the rule is going to be I is equal to 1 to 5, and then here's 3i. So what that particular problem says is sum from terms 1 to 5, and then this is going to be the equation or the rule that generates those terms of the sequence. So if we're doing this by hand, it's going to be 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. Notice that this was my bottom index, and this was my top index. And so I started at the bottom, I ended at the top. Well, if you do that math, you get 45. And so then as I report, the sum from I equals 1 to 5 of 3i is going to equal 45. So really pretty simple. So now let me show you how you do it in your grapher. So I'm going to go to my math button, and I'm going to go down. If your calculator is older, let's miss it, it does not have the summation, and so you have to do it a different way. If you have the little old black guys, their summations will work, but it is very difficult to get all of the information into your grapher, and so I would tell you to borrow one of mine if you have to take a test. All right, so I'm going to hit enter, and notice that it's telling me, so here's my variable, and I started at 1, and I'm going to go to 5, and we had 3x. My calculator is not in sequence mode, so my variables are still x's, and that's okay, it doesn't matter. And then I'm going to hit enter, and notice that there's the 45. So you do have to be able to show the work to do a summation by hand, but you can always check your work in your grapher. All right, let's do our second example. So for example number 2, it says find the sum by hand, and then we're going to confirm with our grapher. So this time our rule is going to be k is equal to 3 to 6, and I'm going to have 1 plus k squared as my rule. So then if I substitute in my values, this is going to be 1 plus, notice on this one that I'm starting on the third term. You don't always have to start at 1. So it's going to be 1 plus 3 squared, and then plus 1 plus 4 squared, plus 1 plus 5 squared, and then plus 1 plus 6 squared. If you wanted to simplify it to put into your calculator, this is 1, 2, 3, 4. So I have 4 plus 9 plus 16 plus 25 plus 6 squared is 36, and that is going to be 90. Okay? So now let's do it in your grapher. So we bring back our handy dandy grapher, and then I'm going to second enter. Actually, let's go back and do it. So math, you have to go down a little bit to get past some calculus fun things. So I'm going to go to summation, I'm going to hit X, and we started on the third term, and then I'm stopping at the sixth, and my equation is 1 plus X squared. Outside the parentheses, go, and there's my summation. Okay, and notice that it takes your calculator a couple of moments to actually do the calculation. Okay, just like with most math things, we have to talk about the properties of summations. So most math things have properties. So here are our properties of summations. It says that if I have I equals 1 to n of a constant, then this is going to be the constant times n. Okay, and C in math is a constant. We actually are just using these equations in calculus right now. If I want to go from I equals 1 to n of C times A sub I, so notice that I have a constant times the rule. I could rewrite this by pulling the constant out front, and then I would have my rule, okay? And then the last property that we're going to have is I equals 1 to n of A sub I plus or minus B sub I. So if I'm summing two different rules, then I could split this up into two separate summations as I equals 1 to n of A sub I, and then plus the summation I equals 1 to n of B sub I. So those are just properties in theory that are to help make a sequence easier to manage. All right, so now we need to get some vocabulary. A series is the whole or partial sum of the terms of a sequence. Okay, so a series is a whole or partial sum. Whole would mean that you're summing the whole sequence. A partial sum would be like the examples that we did in the beginning, where I'm only summing a piece or a portion of an overall sequence. Okay, more definitions. A finite series is going to be the sum of a specific number of terms. And if you think about the summation notation, that means that if I go from I equals 1 to 5 of A sub I, a finite series has a beginning and an end. Okay? An infinite series, on the other hand, is going to be the sum of all the terms to infinity. And Toy Story just popped into my head, to infinity and beyond. Sorry. Whew. Sometimes there's math humor. So a finite series can be graphed. It's actually kind of interesting if you graph a series. So instead of being a connected series of dots, it is a collection of individual dots. So a finite series is going to look linear. Okay? Remember, in a series, it's not technically a line because the area in between the dots is not included. It's only the finite data points, right? An infinite series is going to be a curve. And specifically, the curve is often going to look like, let's see if I can squeeze it in over here. The curve is often going to look like an exponential growth function. So that's going to be an infinite series. Okay? If I had a situation, so let's say this one is the sum from I equals 1 to 10 of 3 over 10 times I, right? This is a finite series. It has a beginning and an end, and this is the rule that generates that particular set of values. On the other hand, if it's an infinite series, I equals 1 to infinity of 3 over 10 times I have the same beginning spot, but this one goes to infinity, and then I have the rule that generates the individual terms. Okay? The interesting thing about an infinite series is that they will often approach kind of a value. And so it resembles, it's not, but it resembles, which is an interesting word, it's going to resemble a vertical asymptote. And so sometimes I can estimate the summation by summing in a really large number instead of infinity, because there's no infinity button on our calculators. And so then I could come up with an approximation of what the infinite series is equal to. So let's do an example. We're going to use the same equation that I just was using. So this says find the third partial sum of I equals 1 to infinity of 3 over 10 I. Okay? So if I want the third partial sum, that's going to be, I'm going to write that out, the third partial sum is equal to the sum of terms 1, 2, and 3. When they tell you to do a partial sum, we assume that you start at the beginning, and in this particular case, the beginning is 1, so it would be the sum of those first 3 terms. So if I was doing it by hand, it would be 3 over 10 times 1 plus 3 over 10 times 2 plus 3 over 10 times 3. And again, this is n is 1, n is 2, n is 3. And if you did that math, you would get 0.3 repeating. And we always go to 3 decimal places, so we would do 0.33 repeating. And this would be the third partial sum. Okay? All right. Let's do another variation on this problem. So for example number 4, it's going to say find the infinite sum. Okay? And so I'm going to have I equals 1 to infinity of 3 over 10 times I. Okay? We will have a formula soon to manage this, and that will be the expectation. But for right now, we're going to talk about this. Okay? This is going to be, did I do that right? No, I wrote this badly. Sorry. My bad. This is 3 over 10 to the I. Okay? So we're going to write it like that, so slightly different. So for right now, since we don't have those formulas, I'm going to estimate by using large numbers. Okay? So I'm going to start by doing 3 divided by 10 raised to the, let's say 10. Okay? And I get 3 times 10 to the negative 10. Okay? And then I'm going to enter, I think I have written this badly. We'll just go ahead and manage it from here. But if I did, for the next estimate, maybe I do 3 divided by 10 raised to the 50, and I'm going to get an even bigger 0. So our infinite sum is going to equal 0. So you can try this. Sometimes it's difficult. In a couple of sections, we will get an exact formula so we can do that precisely. But that is just one way of making our calculators be tricked into doing an infinite summation. And notice that I don't have an infinity button, which is why I'm entering larger values of I or n, either way, to see if my calculator will tell me what the graph is actually approaching. All right, I have one last example for you, and it's an example of a sequence in series, and I'm using it to figure out money. Okay, so I have a deposit of $5,000, and it's going to be made in an account that earns 3% interest compounded quarterly. The balance in the account after n quarters is going to be given by a sub n is equal to 5,000 times 1 plus 0.03 divided by 4 raised to the n. And if you'll remember your compound interest equation, this is the initial sum of money. This is 1 plus the interest rate. This is the compounding period. And then this is going to be time. Alrighty? So the balance in the account. So we're looking for, I didn't write my question mark, the balance in the account after n quarters. So I'm going to enter this handy-dandy equation in my summation, okay, just to show you how that works. I would probably choose to do this problem with logs because I think it's a little bit more straightforward, but I'm going to show you that I can also do it with a summation. Okay, so I'm going to enter, we're going to start at time is equal to 0, because with money we often start with time is equal to 0, so I'm going to say x is equal to 0, and let's say we want to start or stop after 10 quarters, and then I'm going to enter 5,123 times 1 plus 0.03 divided by 4, and then that's going to be raised to the x outside my parentheses. So if we look at what my calculator is doing, we're going to find the balance of money. We're going to start at 0. So we're looking how many, after 10 quarters, how much money do I have in the bank? And I hit enter. And then there is my value after 10 quarters. Okay. Again, I would probably choose to do this with logs or just substitute in values with a regular equation, but showing you that we can use our calculators in a variety of different ways to approach the same problem. All right, that's it for today. I will see you soon.